Hello, in this tutorial we will use RapidMiner to build a decision tree for classification. So the target variable is categorical in this case, and more specifically we are looking at binary classification. And we will go on to examine the accuracy of the model based on the confusion matrix that is generated as part of the performance evaluation process. As an aside, decision trees can be used for target variables that are quantitative in nature, but that will be left for a different tutorial. So very quickly, the way decision tree mining works, you start off with a data set that is impure in that it has records of both categories. We are looking at a binary classification setting. So at the start, you have a data set that has records of both types. And what you do is you recursively split this data set into smaller and smaller subsets based on questions asked about each of the different features. And as you recursively create these smaller and smaller subsets, these subsets get increasingly more pure. That is, they increasingly start having records of one type. And what you should end up with ideally is a bunch of leaf nodes. So after you've asked all your questions, you get a collection of leaf nodes here. And each leaf node consists of records only from one of the two classes. So each leaf node is completely pure. If that happens, your decision tree has done a perfect job of classification. And in practice, that almost never happens. You end up with some nodes being impure, some nodes being pure. Hopefully, a lot of the leaf nodes are pure. Only a few are impure. But so it's less than the classification done by this decision tree will be less than perfect in almost all practical cases. So there are different metrics that one can use to judge the level of impurity of a node during the splitting process. Two common metrics that I use are the Gini index and entropy. So now let's take a quick look at the data set that we will be using. This is from a banking application. The target variable here is the one shaded in yellow. It says personal loan. So the bank recently had put out a campaign where they offered personal loans to their customers, and some customers accepted the personal loan. They are coded as 1, and many, if not most, of the customers declined the personal loan. They are coded as 0. So for each customer, you also have data on many of their features or characteristics such as age, their income level, the number of people in their family, whether or not they have an online account with the bank, whether they have a bank issued credit card, and so forth. So the idea is to be able to classify a customer accurately into one of these two categories. Either they accepted or did not accept a personal loan based on questions asked about these different features of the customers. So with that as a background, let's start up RapidMiner and begin our model building process. See, here is the RapidMiner user interface. Now, before I start the model building process, let me quickly show you the data set. So here's the bank personal loan. And specifically what I wanted to show you is we have about 5,000 records, 5,000 observations. We will split this into a training and a validation subset and then proceed with the performance evaluation. So let's begin the design process. First step, of course, is to retrieve the data. So I drag and drop the data set into the process panel, and that activates the retrieve operation. The next step is to tell RapidMiner which variable is the target variable, and I do that using the set role operator, just like we did in linear regression. So I bring the set role operator over here, and I connect it to the previous retrieve operator. So now when I've highlighted set role, I go over to the parameter panel, hit the drop-down button under attributes, and out of all the attributes, I highlight personal loan. That is the variable, the attribute that is my target variable, and I identify that as the label. That's RapidMiner language for dependent variable or the target variable. So that's the label. So now, unlike in linear multiple regression, I don't have to convert nominal variables to numeric here. All I will do is I will split this data set into a training and validation data set, and then I'm pretty much set to do my modeling. So splitting of the data, so I'll do using the split data operator. I bring that up here, and I chain that with the prior operator, set row. So now I'm going to split the data into two partitions. The first partition will have 70% of the records. The second partition will have 30% of the records. One will be used for training, the other will be used for validation. So I move over to the parameter panel, click on edit enumeration, and by clicking on add entry 2 times, I put in the first partition 0.7, add entry again 0.3. So I have the two partitions, 70% and 30%. And I'm going to specify the sampling type as shuffle sampling, meaning I'm telling RapidMiner, please populate these two subsets by picking observations at random from the original dataset. So my splitting is done. Now I'm in a position to bring in the main operator of this process, which is decision tree. Oh, misspelled it here. Decision tree. So here we go. Here we have the decision tree operator. I bring it in and I drop it into the process panel. So the decision tree, of course, says, where is my training data? How am I going to train myself? I connect the first output port of the split data to decision tree, and I've provided the training data. So the trained model, the decision tree will be outputted from this port, which says model. Okay. Now, if I highlight decision tree as an operator, you can see that there are all kinds of parameters that one can set. Okay. Now, the one that I'll focus on for now is the criterion. What is the criterion that is used for splitting the decision tree? In the slides just prior to building the model, I showed you two different metrics. One was the Gini index and the other one was entropy. So I'll just pick Gini index. No particular reason to pick that. You can see that you have choices. Information gain is entropy based. So I will pick Gini index as the criterion to be used for purity in splitting the nodes. And there are all kinds of other parameters. Do you see maximal depth 10, minimum leaf size 2, maximum size for split 4. So there are lots of options here. For now, since we are beginning, let's leave these other options as they are. We'll come back and revisit them once we have one decision tree going, and then we'll come back and see the impact of those other parameters. So the decision tree has been trained now with the training data. We want to evaluate its performance, and we do that by the apply model operator. So here is the apply model operator. Okay, so it says, where is your train model? It requires 2 inputs here. So the train model comes out from the decision tree operator. So there's the train model, and then it says, where's the validation data? So I connect the second partition to apply model. So the apply model operator will apply the trained decision tree and classify each and every customer that's there in the second partition and predict which category should it belong to, accepted the loan or did not accept the loan. And then we will compare the predicted category with the actual category and see how well the training went or how well the decision tree is performing. So now I'm in a position to judge the performance. So once the trained model is applied, and I have my actual and predicted categories. Okay, so but the performance will be measured using the performance operator. Now since there are a whole bunch of performance operators, we need to be careful to pick the right one. Since we are looking at a binary classification context, I will pick the binomial class performance operator. So I bring that in, drop it into the process box. So it says, where will I find the actual and predicted classes? I find that from the output of apply model. So I connect these two. Okay, so now since we are looking at a binary classification context, there are a number of different metrics that one can use based on the confusion matrix. You can go back to my tutorial on logistic regression to see those again. So I will pick accuracy, which is already chosen as a default, and I will choose 2 other performance measures. One is sensitivity and the other is specificity. Okay, and they can just pick 3 performance metrics just to see how the classification performs. And now I will connect various output ports of different operators to the results so that I can see. So of course I want to see how well my decision tree performed. So I connect the performance output port to results. Okay. I also want to see the examples, meaning I want to see the actual category and the predicted category. So not just the summary performance, but observation by observation, what was the actual category and what did the model, the decision tree model, predict should be the category. Okay. And I also want to see a decision tree is very visual. It's good to see it as a tree. So I want to actually see what this tree looks like. So I connect model to results. Okay, so let me move this around a little bit. So now I have the process set up to actually run the decision tree on the training data and extract the decision tree, mine the decision tree from the training data. So let's run the process now. So here's the decision tree that resulted, and it's quite a big tree. So let me scale it down. For starters, it's really not necessary to go to every node to make the point that I'm about to make. So I'm going to scale it down. I'm scaling it down just to get the whole tree in the picture, simply to show you how fine-grained the tree is. So you can see, without getting into each and every node, that it's a very detailed tree, lots of splits and lots of leaf nodes. Okay, so this is a pretty unwieldy tree to understand and digest. But let's first look at its performance. So if I look at the performance vector, the output, that particular tab, so there are a number of different metrics that one uses when you're looking at binary classification models. So we picked 3. So I'll pick the most common one, accuracy. So what proportion of the observations in the validation data set were classified correctly. Okay, so the accuracy is simply these two diagonals, 1342 plus 1115 divided by the total number of observations. Okay, so you can see that the overall accuracy is very high, is 97%. So the model did a pretty good job of classifying. And if I look at it category by category, so for category 0, that means the customers who did not choose a bank loan, who chose not to accept the loan, the personal loan offer, the accuracy is 99%, is very good. And then if you look at the second category, those customers who accepted the personal loan offer, the accuracy is not as good, of course, but it's not too bad. It is not too shabby. It's 76%. There are situations where the accuracy in one category is 99% and in the other category is 5%. Okay, so here the accuracy in the second category, that is the category of people who actually accepted the loan, is worse, but it's not too shabby. But the main issue here is that the model itself, the tree, is very hard to digest, and it's very detailed and fine-grained with lot of leaf nodes. Now, why did that happen? Why such a detailed tree? Now let's get back to the design and let me highlight decision tree again. Remember, I told you that there were certain parameters here that we chose to leave at their default value. Let's take a look at what these defaults are. So you can see here, says minimum leaf size of 2. So we are saying it's okay for the mining algorithm to create leaf nodes that have only 2 records in them. So imagine that we have thousands of records in the data set. If we allow the mining algorithm to create leaf nodes that have only 2 records in them, we are inviting a tree that is very fine-grained in nature. Okay, so let's play with these 2 parameters and see if we can get a more compact decision tree that's easier to comprehend without losing too much by way of performance. So I'm going to increase this minimum leaf size to 5. If I increase the minimum leaf size, and let's say we have 2000 observations, obviously we should end up with fewer leaf nodes and the tree will get shallower and more compact. That's intuitively what ought to happen. So I'll increase the minimum leaf size to 5, and the minimum size of the node to split, instead of 4, I'll increase it to 10. So I'm getting more coarse in my splitting. That's informally what's happening. So So let me run the mining algorithm again. And now I'll scale the tree down for, once more, just to get a sense of what's happening. So if you look at this tree, I don't know if you can observe, it doesn't look a whole lot less complicated than the one before. It seems to be just as detailed, but in fact it has simplified a little bit, both in terms of depth and the number of branches, but not a whole lot. Okay, now let's see what has happened to the performance. You can see that the performance has not degraded a whole lot, just a little bit. So it has gone down to 96.4%. I believe in the previous iteration it was 97%. Now if you look at the accuracy for the second category, where the customers actually accepted the loan, it has dropped down from 76% to about 75%. So there has been a little worsening of the performance. However, the tree is getting easier to absorb visually and to understand. Okay, so let's take this line of reasoning a little further. Let me make the minimum leaf size to be 10, and the minimum size split I will make 20. Okay, so I've gotten even more coarse in the splitting process. Let me run the mining algorithm again. Now look at what the tree has done. The tree is much simpler. It has fewer leaf nodes, hence fewer branches, much easier to comprehend. There are fewer questions that have been asked. So, and in terms of interpreting the output visually, so you can see this box which is completely blue. That means this is a leaf node which is completely pure. And if I put my cursor on that particular node, you can see the distribution. So there are 2,636 customers in that node of type 0 and 14 customers of type 1. So it's a completely pure node. Similarly, you can see here, this node is it appears to be completely pure. Yes, there are 216 records of customer type 1 and 0 customers of type 0. But the other nodes are impure. So if I look at this particular leaf node, there are 11 records of customer type 0 and 9 records of customer type 1. So what this means is my decision tree has not done a perfect job of classification, but the tree that I'm seeing before me is much more comprehensible. It's much easier to comprehend than the two trees that you saw before. And the way we manipulated the complexity of the tree is by looking at the parameters that one can set for the decision tree operator. But let's look at the performance vector and see if there has been a whole lot of worsening. So notice that the overall accuracy has dropped from 98% in the first iteration. It has dropped only to 96.6, and the accuracy for this category, where the people actually accepted the loan offer, has dropped from 76 to 68. So there has not been a whole lot of worsening in terms of the accuracy, the performance, performance of the decision tree. So I've shown you how these two parameters, the minimum leaf size and the minimum size for the split, can affect the complexity of the tree that results. So in this tutorial, I've shown you how to mine a decision tree from a data set for when the target variable is categorical, more precisely when the target variable is binary in nature. I've shown you how to examine the accuracy of the resulting model, and by playing around with some of the parameters of the decision tree operators, you can achieve some kind of a trade-off between the complexity of the tree that results and its performance in terms of accuracy. Thank you for your attention.